Okay, so this lecture is going to be a bit more relaxing. I'm just going to give a brief introduction and an overview to this rapidly growing area of machine learning, which is deep learning using deep neural networks. So I'm going to talk a bit about the history behind the neural networks and why deep learning became so successful recently. I'm going to talk a bit about main advantages, some problems that were overcome in the recent years, and basically try to give you an idea of what this does that is different from the classical machine learning algorithms we've been seeing so far. And then I'm going to give just an example of application, autoencoders, to illustrate some applications of deep learning. But this is a very broad field, so this is not meant to be exhaustive. I'm not going to cover even a small fraction of what you can do with deep learning. So let's start with a bit of history on artificial intelligence and neural networks. Neural networks have been around from the beginning of the AI movement, even in 1943 with the model of the neuron, how to represent a neuron mathematically. And in the late 50s, Rosenblatt created the perceptron, which was actually not a simulation on a computer, but an actual machine that had the learning algorithm and could learn to identify things, classify examples. And this seemed very promising because they were inspired on the way human brains worked, modeling the neuron and then using that to actually learn something. And this seemed to be a revolutionary way of making machines intelligent and so on. But in the 60s, it was found that if you use a neuron, so the perceptron like Rosenblatt created, is just a linear model. So there is not much you can do with that. This is basically the same as logistic regression and nothing else. And a big problem that they had at the time was that there was no way of combining neurons in sequence and still figure out how to train them, how to compute the parameters. However, during the 70s, the backpropagation algorithm started to appear in other contexts, and in 1986 it was demonstrated that it could be used to train networks with multiple layers of neurons. So now these things started to change and artificial neural networks started to come back. But that period between 1960s and late 80s was very bad for artificial intelligence in general, and in particular for artificial neural networks, because there was a lot of hype in the beginning, a lot of great expectancies for what artificial intelligence would do, but then a big disappointment when they failed to do any of those things. But then in the 90s, AI started to shift from the more logic oriented and knowledge driven approaches to approaches based on data, especially with new machine learning algorithms. For example, in 1992, Vapnik published the kernel trick for support vector machine, and now we had more or less this scheme that we could apply in general, which is we have some features. We do a nonlinear transformation, which support vector machines can do very cheaply using the kernel trick, as you know. And then we can use a linear classifier in this space where our features were transformed non-linearly, and this can do things way beyond what a simple linear classification could do. So support vector machines became very important and widely used, and in parallel also multi-layered neural networks, convolutional networks, and so on also started to be used for some applications because they could do these nonlinear transformations too. In the late 90s, the MNIST database was created, and this became one important benchmark, but other benchmarks started to become available. And this was also very good for machine learning, for helping to develop new algorithms, test them, compare them, and so on. And now, more recently, we have more advances. So in the early 2000s, 2007, so on, there was this idea of extending the depth of artificial neural networks using pre-training. So we could train each layer individually first, and then stack them together and just fine-tune the whole network. This was experimented with, but what really revolutionized artificial neural networks was a change to these rectified linear units for the hidden layers. I'm going to talk a bit more about those, but this really made a big difference. This better optimizers for training the network, and also hardware. So using general purpose graphics processing units, or even tensor processing units, so processing units specially designed for implementing neural networks. This gave a lot of computational power, and it's what powers the big neural networks that we have today. So what this brings us that is innovative relative to what we saw with classical machine learning algorithms is that we have a stack of many nonlinear transformations. So when we have a deep neural network, we have many nonlinear transformations, and we can actually skip the early stage where we choose the best features. We just transform until we reach some point where the last layer just does a linear classification, and we get the result that we want. So basically, when we do that, for example, for images with convolution layers, we can see that the first transformations are focusing on more detailed and elementary aspects of the image. For example, horizontal edges, vertical edges, obliquous edges, and things like that. And then as we go on further along the network, it starts identifying more complex patterns. And at the end, we basically have representations that are identifying features like eyes and ears and mouth and so on, and the linear classifier can use those to do its job. So we saw an example of this with solving the exclusive OR problem. This is something that the perceptron, the original perceptron, which is just one neuron, would not be able to do, because if you have this set here where 0, 0 or 1, 1 is red, so in this case false, and this 1, 0 and 0, 1 is true, you cannot use a straight line to separate these two classes. But if we pass this on a first layer that transforms the data, it can squeeze these two negative, the red ones, over to one side, and then it's easy to separate the two. So if we represent the problem here, this is the exclusive OR problem. If you consider this to be the one, the black box, this is 1, 1, the 0, 0, it's false, 1, 1 is false too, and then 1, 0 and 0, 1 here, you have the true values. But these are the four corners that you cannot separate with a single line. The mid, the hidden layer on the network does this nonlinear transformation and basically separates two cases where they have different values, and these become one at the end. So this would be, for example, these corners here that have one coordinate at 0 and another at 1, for example, and these other values where the coordinates are the same. So by spreading out the examples in different places using this nonlinear transformation, the problem now can be solved. Of course, it can be solved in many different ways. It doesn't matter if you put the red ones on this corner or on that corner or on that corner. The network will converge to different solutions, but all that matters is that the nonlinear transformation allows then a linear classifier, which is the last neuron, to solve the problem. And you can add this in many layers. So for example, if we have these clouds here, we want to separate the red from the blue. We have one layer that is doing this transformation, then the other layer picks up this first one and does another transformation, and the last neuron can now put most of the red ones on top and the blue ones here and separate most of these examples because of the different separations here in the hidden layers. So you can imagine that if we can do this with many layers, we can move or greatly transform whatever data that we have. So this is what led to deep learning becoming so successful, as long as you have enough computational power and a sufficient number of examples. Because as we increase the complexity of the model, we increase the number of examples we need in order to avoid overfitting. So, for example, in 2006, there was this challenge, the Caltech 101 image classification problem. It had 101 categories and about 50 images per category. So they range from 40 to 800, but on average it was around 50 and about 100 different classes of images. And so this was a computer vision problem trying to figure out which object there was in each photo. So classical computer vision models using classical machine learning and feature extraction and so on had about 26% error. The computers were slower at the time, but basically neural networks are not very good for this. But then in 2012 we had this ImageNet dataset. They have 1,000 categories and 1.2 million images, and also general purpose GPUs became available for computation. So from this point on, large convolutional networks became dominant in image classification. And basically, you can see that in 2012, they had a 15% top 5 error. So this is the error when trying to place the correct image in the top 5. Then in 2013, it went down to 13%, 7%, 6%, and currently it's about the same level of mistakes that humans do. So basically the neural networks are making mistakes on the same level of the actual errors in the labeling of the images. So at least for this kind of problem, they became almost as proficient as humans. And there is no other algorithm that can approach deep convolutional networks for image classification at the moment. And this is basically what makes the difference. If you have fewer data, then deep neural networks are very bad. They overfit too much and they don't perform well. And you can solve the problems better with classical methods. So this is what happened when they had few images and few categories, and you were somewhere around here, where classical machine learning and computer vision models worked fairly well, but deep learning did not work with so few examples. But as you start increasing the number of examples, then the added power of deep models is now compensated by the larger number of examples. You have less problem with overfitting, and basically you can surpass the traditional methods because those models are a lot more limited, and so that's why deep models dominate a lot of these areas today. So basically, areas where you have a lot of data, deep learning becomes much better than the classical models in machine learning. But note that if you don't have much data, then deep learning does not work. You cannot train a deep model if you don't, at some point in the process, there are things like transfer learning where you can go from large data sets into smaller data sets and things still work, but at some time in the process you need a large data set to train your model. So this is an example of what a deep net is. This is Google Net from 2015. These are all the layers that you have here. They are separate in different blocks. There are connections between that skip some layers and so on, and different outputs and so forth. So the architecture is very complex, and the network can be very large. These networks can have hundreds of millions of parameters to fit. So one thing that we gain with deep learning is we don't need to do feature extraction. This is basically, in practice, one important difference. For classical approaches, when you have to work with, say, text documents or images or things like that, you need to find ways of extracting features. You saw a very simple example of that in the second assignment, where you need to take from all the pixels on the image, you need to extract some features in order to work with them. So if we want to do this and want it to work really well, we need to spend quite some effort in finding the correct features, the best way of extracting the features, and finding, for example, histograms, detecting edges, things like that, finding the appropriate words, clustering the words. And this takes lots of work and lots of understanding of the data, and can take years to master. With deep learning, we do things differently. So these classical machine learning approaches start with the feature extraction step, where humans, the engineer, decides which features to use, and then does some nonlinear transformation, usually for the classifier, like in support vector machine, something like that, and then classifies that. With deep learning, we just stack many nonlinear transformations, and we don't care about any intelligent feature extraction. We just stack these transformations until we have enough of them to get the correct features for classification. So this is basically what you can do with deep learning, instead of, for example, using support vector machine that is very good at doing the nonlinear transformation step, but you need to have some useful features for that. You can just stack a lot of layers on your network and feed in the raw data into the network. So you can just put in the image, and then it will do all these transformations until it gets one representation that is useful for whatever you want it to do. So, for example, with image classification, you get different layers doing different representations that start to capture at increasingly complex aspects of the image, until when you reach the last layer, you have everything set up to make it easy to determine, for example, if it's a cat or a bus or a car or something like that. This with the neural networks, there is this universal approximation theorem that tells us that all you need is just a single hidden layer, and you can locally approximate any function. So in theory, if you had a neural network that had just one single hidden layer, you could map any relation between the input and the output. However, this does not tell us how large that single layer would have to be for any particular case. So if you wanted to try to train a neural network with just one single hidden layer to classify images, you probably would need such a huge single hidden layer that you would never have enough images to train that. With deep networks, you can have fewer neurons per layer, but you can still have a higher Vapnik-Chevronensis dimension, because as you have these nonlinear transformations stacked, they can oscillate very quickly from one layer to the other, and these oscillations can allow us to shatter the different sets more easily. So you can have networks that have a higher power to classify examples, using stacks of layers, of smaller layers, instead of having a very large one, and still with the stack have fewer parameters than you would need with a very large layer. So this is why, at least in theory, why the deep networks work a lot better than just trying one very large, wide but shallow neural network. But one problem that prevented this from becoming so successful until recent years, apart from the availability of data, but there is an additional problem, which is the problem of vanishing gradients. If you recall from backpropagation, what we are doing is adjusting the weights at each particular layer by multiplying the derivatives of so the partial derivatives of the error function and of the functions of the activation function and of the weights of the layers in front and so on. So you see, we are doing all these multiplications of derivatives and going backwards all through the network. If any of these derivatives is very small, so close to zero, then the product of everything drops down to zero. And this is the problem of vanishing gradients. When the derivatives approach zero, then backpropagation stops working, because when we multiply all of these things, we get a zero and we cannot update the weights. All the weights become stuck, and so the network does not learn. So this happens with many classical activation functions. You can try this in TensorFlow Playground if you go online. Sorry. And for example, you can choose some data sets and then create your networks and try to train them. And if you use a sigmoid activation here, things work fine with this data set. We have one hidden layer, and the network trains to properly separate these two classes, the blue and the orange one. If we have this more complex data set, then this hidden layer does not work. We can add more layers, but then even training a lot of epochs, it still isn't able to solve this problem. So what's happening here is that adding these additional layers is only making training harder because of the way the sigmoid activation works. If we go away from the midpoint here, the function, the slope of the function starts to go to zero. So the function starts to be constant, either at 1 or 0. And so the gradient, the derivative, will approach 0. And if this happens at any stage during the backpropagation, then the derivative disappears and backpropagation stops working. So if you try to stack layers with this kind of activation functions, even though they look very nice for computing the derivatives and so on, because they are continuous, the derivatives are continuous and so forth, they have this problem. The derivatives tend towards 0 at the extremities, and when that happens, backpropagation gets stuck. So this is where the rectified linear unit came into play. This kind of activation, like sigmoid or hyperbolic tangent, this is another one that was widely used before. They have this problem that they become constant at the edges, especially at this part when the neuron is firing. And so if you saturate the neuron, then the derivative becomes 0. The rectified linear unit has this shape. So this is a very simple function. If x is greater than 0, the output is x. If x is smaller than 0, the output is 0. So this is just two straight lines like this. Now remember that if we were doing this, if the output is also x, this would not be useful, because if you stack linear transformations, you just get a linear transformation. You need a non-linear transformation in order for this to work. But this elbow here gives us the non-linear transformation. This is only linear on this part, and then it's non-linear on this part here. It's a different slope on this part here, and basically this edge here makes it non-linear. So that is the secret for deep neural networks, basically. There are variants of the rectified linear unit, but what happens here is that if the neuron is firing, the derivative is constant, is equal to 1. It doesn't matter how strongly the neuron is firing, the derivative is also always 1. And if you use this kind of layer, so if you use sigmoid with 3 layers this doesn't work. The training gets stuck. Here are 1,472 epochs and it did not learn. But if you use rectified linear units, then after 270 epochs, it already managed to classify the set pretty well with 3 layers, and you can add more layers and it still works because there is no problem with the vanishing gradients. So if you go to the TensorFlow playground, you can actually experiment with this online and see the results for yourself. Okay, so let's see just one specific example of what you can do with neural networks, which is autoencoders. Autoencoders are a special case of neural networks where you can actually do unsupervised learning because you don't need labels in your data. So you can use lots of data, unlabeled data, which is usually cheap, to train autoencoders. And the idea is that you are training a neural network to output the same thing as you input into the network. This appears to be a bit silly because you're just getting the same thing that you put in, but the magic is happening inside the network. If you add some kind of constraints to how the network can go from the input back again to the same data, then you can use the network to create an encoding that describes the input in some way that you want. And now you have many different possibilities here. But basically, the idea of the autoencoder is that you have this encoder part that is mapping from the input into this latent space of your network, so this inner code. And then you have the decoder that maps back from this latent space into the original input space. So you can see the network as a combination of the two, the encoder and the decoder. Now what you're doing is you don't need any labels because you're just training the network to give you the same as the input. So basically you're computing a function, the decoder function, that when applies to the encoder of x gives you back x again. This may appear not to be very useful, but if you constrain this latent representation in some way, you can do things like reduce dimensionality, compress data, capture some structure, and do lots of useful things. So let's see some ways of how we can do this. But basically, we just have a feed-forward network. The autoencoders are feed-forward networks that have some bottleneck that will force a useful representation of the data. And this I find this very interesting because this seems to be closer to the way we actually learn. So if you look at how other examples of machine learning works, is that you give labeled examples and you train the model to give you the labels. But this is not how we learn as children. We do not look at many different pictures labeled cat and dog and things like that to learn what cats and dogs are. We just look at cats and dogs and we learn with unlabeled examples. So this may bring us a step closer to what actual learning and intelligence may be. So let's see different types of autoencoders. One example is an undercomplete autoencoder, which has the code in the middle, has fewer dimensions than the input. So we have to learn how to get the input back after encoding, but the encoding has fewer dimensions. If we used just a linear autoencoder, this would be similar to PCA, but without those constraints that the vectors have to be orthogonal. But since we are using nonlinear transformations in our network, this goes way beyond what principal component analysis can do, and we can have much more powerful representations. Of course, we can overfit if we have a very powerful autoencoder and not enough examples, then the autoencoder can just learn a table that if it's example number 1, it's this one, if it's example number 2, it's this one, and so on. So we don't want to do that, but if we can fine-tune the autoencoder, we can get something like this. This is actually a classical example from the 90s, Mitchell's autoencoder. We have these inputs. There are 8 inputs, and one of them can be a 1 and the other 0. So the 8 possible inputs are these 8 combinations. And then we are training this network to give us the same as the output. But we will be looking at these 3 neurons here. And these 3 neurons will now give us different combinations of high and low values that correspond to the 8 different combinations of bits that we need to use with 3 bits to get these 8 different combinations. So basically, we are getting the representation of the 8 different values as 3 bits of 0 or 1. So this would be using an autoencoder, an undercomplete autoencoder, to reduce dimensionality. Another possibility is to use an overcomplete autoencoder, so one that has larger, potentially larger dimension here, but adding some additional constraint. For example, we can use regularization in a contractive autoencoder. We use regularization to minimize the derivatives with respect to the input. So the derivatives of the activations of those neurons with respect to the inputs. This means that the encoding is less sensitive to small variations in the input, and will allow us to capture better some aspects of the distribution of this input. For example, if we use these contractive autoencoders on these kind of images, we can have neurons that are specialized in different aspects of the image that may be more meaningful, rather than, for example, if we use PCA, then each direction will be determined just by the variance of the different pixels in our data set and so on. And so it will not represent anything particularly intuitive or useful in the image. Another example is to have sparse autoencoders, where we may have many neurons in the encoding, but we only want a few of them to be fired at each time. So we can use this regularization penalty as the divergence between the actual number of times the neurons are firing and the probability we want them to fire with. So suppose we only want 10% of the neurons to fire for each example, and we give a penalty if the number of neurons firing deviates from those 10%. Now, what happens in this case is that different neurons will become specialized to find different aspects of the input. So in this case, we have images that were just 10 by 10. We have 100 neurons on that central layer, the encoding for the autoencoder. So we are not reducing dimensionalities, but we use sparseness by forcing only a few of them to fire depending on each image. And now we can see which images cause neurons to fire, and we see that they specialize on different types of aspects of the image. So these diagonals, these vertical lines, bright lines, dark lines, and so on, the different neurons are specializing in identifying these different elements, and so each image becomes just a combination of different elements in the encoding. You can use autoencoders for denoising. For example, if you have the original images without noise, you can input the images adding random noise, for example, putting some pixels in white or changing from white to black, and put this in the encoder and force the autoencoder to give you back the original image. Now you do this over and over again to train the autoencoder, so that the autoencoder learns to take an image that has some noise or some censored part or something like that and reconstruct that from the original. So you can use this to remove noise from images, remove parts of an image where you have an object that is covered by other objects or things like that, as long as you train the autoencoder with enough examples to do that. Variation autoencoders are also very interesting because in this case you are not computing the actual values of the encoding, but the parameters of random distributions that will encode your images. So you can actually use variation autoencoders then to generate images of the same type, because they learned the distribution, the parameters of distributions. For example, mixtures of independent Gaussians. This means that the encoder is actually not giving some fixed values for encoding the image, but, for example, the means and the standard deviations of Gaussian distributions that can be fed into the encoder to generate cats that are similar, for example, to the cat that was input, but they may not be exactly the same. And this, the way this is done is with this trick that can help us backpropagate the error, even though we have a random step here. So if we just have the encoder with for example, the mean and the standard deviation of the Gaussian distribution, and then we roll the dice and we get a random value here, we would not be able to backpropagate the error, because here we have a random value and we cannot compute the derivative there. But what we can do is to have, this is just the mean and the standard deviation, and this is a random value with a normal distribution, 0 and 1 standard deviation, that gets multiplied by the standard deviation before adding to the mean. So we cannot propagate the derivative over here in this branch because this is random, but we can propagate the derivatives over this part, which is what matters. So actually you can train these networks with backpropagation and compute the parameters for the random distributions, even though this step has a random distribution and so is generating different examples all the time. This is what you can get with variation autoencoders, because you can, by also choosing the distributions here and forcing them to become as independent as possible, you can disentangle different attributes of the data. For example, this is a variation autoencoder trained on the MNIST dataset, and we have two neurons in the encoding that specify, one of them specifies which is the digit that you're going to write, and the other specifies the style in which you're going to write the digit. So you can generate new digits by combining the digit and the style. For example, a 7 with this style, or this style, or this style here, or a 5 with, or using this style for the different numbers and so on. And you can generate similar numbers using those styles and the content at random, but they will keep more or less the same style and the same content in this case. This is another example for faces where you have different people and then different styles of faces, and you can represent the same faces in the different styles. You can also use, these are examples of convolutional autoencoders where you can use convolutional layers to map between images in the input and images in the output. So in this, most of these examples I've been given was this kind of autoencoders because visually they are more appealing. And one example of this is to do deepfakes. So this is one way you can do deepfakes with autoencoders. You have a video of a person, for example, Jimmy Fallon. You take lots of images of the face and you distort the images. So you cause some distortion on the image and you train the autoencoder to give you the original image without the distortion. This allows you to amplify a lot the data set that you have and train the autoencoder with many, many examples. And the autoencoder can fix some problems on the distortion, orientation, and so on. But now what you're going to do is to take images from other person, for example, John Oliver here, and you're going to do the same thing, but you're going to use the same encoder for both. So this part of the network is encoding both the Jimmy Fallon and the John Oliver distorted images into the same encoding, and then you use different decoders to generate the Jimmy Fallon and John Oliver original images. So this way you are training one encoder and two decoders with this data set in parallel. And now what you can do is to use images from one in the encoder. For example, you use the image of Jimmy Fallon in the encoder, and then you use the John Oliver decoder to get back the image. And this translates one face into the other and inside the video. And since you trained both the decoder and encoder to fix any distortions and so on, this network can handle the changes in the orientation of the images and such. So this is one way of creating deepfakes, where you can just replace the face of one person with another, or the body, or the voice, for example. This is using images as example, but you can use voice. And there is at least one case that I know of where they use deepfake to fake the voice of the director of a company, and then have used that to call the accountant and have money transferred to a different account. And so they managed to take some money from the company by faking the voice of the CEO. So this can have some bad applications. Also, if you go to pornography sites and so on, you can find many deepfakes. That's one motivation for a lot of content on the internet, and a lot of research into, at least amateur research into this kind of technology. But this is something that is starting to become very well known, because it's very easy to do if you have, especially if you have video of two persons, because then you have lots of examples, lots of images to train the network, and you just train the encoders in common and the decoders for each particular person, and it's easy to do the replacement there. Okay, so this was just a brief overview of deep learning to give you an idea of this stacking of nonlinear transformations. The reason why there is this big success recently, both the progress of techniques and the availability of data. And there are many different applications here for text generation, voice recognition, identifying images, autonomous driving, things like that. There's a lot of fields of application for deep learning. I just gave an example of autoencoders because I like autoencoders a lot, so this is personal bias, but there are lots of many different applications. If you want to read more about this is the textbook I follow on the deep learning courses, so there will be on the next semester, if you're interested, both for computer science and for big data. They are different courses, but they cover these parts of deep learning and similar things. Okay, so this is all for this semester. I will log into the Zoom call now if you have some questions, and we can talk a bit. See you soon.